Hi everyone. In this video, we will continue our discussion of line integrals by looking at some basic properties of the line integral that follow from the definition. In the previous video, we defined the line integral, and we looked at an example in which we calculated the line integral of a vector field over two different curves, and for one of the curves, over two different parameterizations of those curves. At the end of the video, we concluded with two major questions. And in this video, we want to address the first of those questions, which was, are line integrals independent of parameterization? So we observed last time that for two of our parameterizations, the parameterizations we called alpha 2 and alpha 3, of the same curve C, we got that the line integral of f with respect to the curve, the parameterization alpha 2, and with respect to the parameterization alpha 3, we got the same line integral for both parameterizations. So you can see here, I have used this notation to emphasize that these are line integrals over the same curve. We simply here are using two different parameterizations. Now, that was, of course, just for a particular vector field f, and for two particular parameterizations, alpha 2 and alpha 3, of a particular curve C. So there's no reason to believe that just based on that one example, this is true in general. So we want to explore this a little more in depth in this video. Now, before we can begin to formulate some sort of theorem about the independence of line integrals with respect to their parameterizations, we first need to think about what we mean by two parameterizations of the same curve C. So as we've written it here, you could think, okay, well, alpha 2 and alpha 3, these are both parameterizations of the same curve C because the graph of alpha 2 and alpha 3 are the same. And indeed, if we go back to that example from last time, so last time we were looking at one parameterization, the parameterization alpha 2 of t was t squared I plus t cubed j. And the parameterization alpha 3 was ti plus t to the 3/2 j. So both of these, and these were both for t from 0 to 1. So we note that both of these parameterizations began at 0, 0, ended at the point 1, 1. Okay. And both of these curves have graph y is equal to x to the 3/2. So certainly both of these parameterizations give us the same graph. They also both happen to start at 0, 0 and end at 1, 1. Okay. And notice also that they both start and move without stopping towards 1, 1. So all of these things, it's not clear which of these are necessary for two parameterizations to be considered equivalent and which are maybe just particular phenomena here. So the first thing we have to do is actually define what we mean by two equivalent parameterizations, right? So it's probably not going to be enough just that they give us the same graph, because you can imagine a parameterization which gives you this graph, but say wanders back and forth a lot. It re-overlaps itself. And if you do a lot of that, and maybe you come up here, and then you come all the way back, and then you go back halfway and come back, like these all give you the same graph, but somehow that parameterization feels very different than these two, which start here and move here. They just sort of do so at different rates. So we need to carefully first define what we mean by two equivalent parameterizations. Now, at first, it's going to be a little hard to tease out what exactly some of these conditions are doing. So we'll carefully, once we write down the definition, we'll carefully walk through and try to understand what each condition is saying. So we say that two parameterizations, alpha and beta, so I'm imagining that alpha is a parameterization from the interval AB into Rn, And beta is another parameterization from CD into Rn. So again, potentially they're mapping different closed intervals of R, right? But they're both mapping into Rn. I'll say these parameterizations are equivalent if there exists a differentiable function u. This u we're going to think of as sort of a change of variable or change of parameter function. If there exists this differentiable function u, which maps from CD into R, such that u prime is not equal to 0 for all t in CD. So notice, right, if u prime is never equal to 0, that means u prime is either always positive or always negative. Okay. The range of u is equal to AB. So notice up here we said that u maps from CD, so it has domain CD into R, but here we're saying specifically that it must map into AB. So all the outputs must be in this interval. And because we're saying the range is actually equal to this, we're saying that every point in the interval AB is hit. Okay. So our range, the things that we hit are precisely all of the values between A and B. And then finally, and this is the key to sort of the change of variables piece, we want beta of t to be equal to alpha of u of t for all t in the closed interval CD. Okay. So as we state this, really what we're looking for this differentiable function u. This u is our change of parameter. It sort of explains how alpha and beta are related to one another, despite the fact that they're sort of mapping from different intervals. And we want to find this change of parameter such that it's differentiable. Its derivative is never 0. Again, that really means that your change of parameters is either always increasing or always decreasing. And you want it to hit every value between A and B. So as we think about this function u, this function u is taking inputs in the interval CD, and it's spitting out values between A and B, right? Because it's going to take, beta takes inputs between C and D. This u function is going to tell you, okay, when the parameterization beta is at C, what value is the parameterization alpha at, right? It's at u of t. Okay. So there are only really two possibilities here because my u of t has to either be increasing or decreasing because the derivative is never 0. Okay. So either my function u, I have to hit every value between A and B. So either always am increasing and I start at A and I go up to B. Okay, that's one possibility. Okay. So in this case, u of C is A and u of D is B. And that's one possibility. Or, of course, the other possibility is I go from CD to A, B. My function, I don't know whether it's increasing or decreasing. I just know that it's always one. It's only one of them. So it's also possible that I flip this the other way around and u of C is B, and then my function is decreasing to here. But one of these, I must be in one of these two situations. Now, the concavity of these things, right? What I can't do is I can't oscillate, right? I can't do this because if I did this, I would have some point where my derivative was 0, right? So it's either always increasing or always decreasing, but the concavity could change in between. So these are sort of representative examples, but certainly far from the only possibilities here. Now, to maybe make this a little more concrete, right, you could consider the following example. What if we let alpha of t be sine of t, cosine of t, and let's say we do that for t, let's see, I'll write that down here, for t in 0 pi. And what if you also had beta of t as cosine of t sine of t for t in minus pi over 2. to pi over 2. Now, you might have to play around with these a little bit, but what you'll actually find is that if you were to graph both of these parametrically, what you would get is the right half of the unit circle. Okay. You have your three sort of standard points here. So there's 0, 1, 1, 0, and 0, -1. Okay. So each of these give you the same graph, right? This curve C. The question is, can you find a differentiable function so that beta of t is equal to alpha of u of t? Okay. Now, as we start thinking about what that might look like, right? If I were to just sort of trace out this alpha, so when t is 0, this gives me the point sine of 0, cosine of 0, or 0, 1. Okay. And then it starts at this point, right? And I can check through some points if I want, like what happens if I'm at pi over 2? Well, sine of pi over 2 is 1. Cosine of pi over 2 is 0, so that gives me 1, 0. So alpha is moving around the curve in this direction. Oops. What? I'm not sure why I keep writing E. There we go. So our parameterization alpha is moving us around the circle in this direction, starting here and moving down here. The parameterization beta, if I look at this, this looks like the normal parametric form for a circle, right? And so this is just going from the angle pi over 2, negative pi over 2 to pi over 2. So beta is moving us around the circle in this direction. Okay. Now, again, both are carving out the same curve. They're just doing so in opposite directions in this case. Now, in this particular case, we can find such a u of t. We just need to use a little bit of trig. And one of the things I may ask you to do for homework is just to sort of verify that this works. But if I take u of t to be pi over 2 minus t, then I can show that if I plug this in, so I consider alpha of u of t, I can show that this is equal to, so I would just plug in here what those values are, and I would get that that was equal to beta of t. Okay, so these are, in fact, equivalent parameterizations. In this case, even though they sort of start at opposite ends, they each just carve out the curve one time. They just happen to be moving in opposite directions. Notice one way you can tell that these are moving in opposite directions is by analyzing this function, and in particular, noting that this function is decreasing, right? So it's moving opposite ends of the curve, right? It's moving from opposite ends of the curve to opposite ends of the curve. So in general here, right, since u prime of t is negative, that implies that these are moving in the opposite direction. Whereas if u prime of t was positive, that would imply that they're moving in the same direction. Okay. Again, you can see that from just here. I mean, you can think about it in terms of these graphs of u of t, but if you also think about it here, if these are moving in the same direction, then alpha prime and beta prime should have the same sign. If you apply the chain rule here and take derivatives of both with respect to time, you'll see that it depends on the sign of u prime, whether or not these things, alpha and beta, have the same sign. Okay, so that's where we can understand more about this by looking at this change of parameters u of t. Okay, but the moral of the story here is if we have this change of parameters u of t that satisfies these conditions, then I have two equivalent parameterizations. And now it might be reasonable to expect then that my line integrals over that curve, as long as I have equivalent parameterizations of that curve, that my line integrals over that curve are the same. Okay, so what we want to do then is state that as a theorem formally, and then we want to prove that theorem. All right. So here's the theorem. Let alpha and beta be equivalent piecewise smooth parameterizations of a curve C, then the line integral of the vector field f over C with respect to the parameterization alpha is equal to the line integral of f over the curve C with respect to the parameterization beta if alpha and beta trace out C in the same direction. And the line integral of the vector field f over the curve C with respect to the parameterization alpha is equal to negative the line integral of the vector field f over the curve C with respect to the parameterization beta if alpha and beta trace out the curve C in opposite directions. So what we see here is that we get almost an equivalence, but we have this difference of sign, which really depends on whether your parameterizations trace out the curve in the same direction or in opposite directions. Now, sort of an immediate consequence of this, right, and it's probably not surprising, right, is if we take the parameterization to just move in the opposite direction, right, we get negative the line integral as if we went in the other direction, right? So if you just swap directions, right, you're just going to swap the sign on your line integral. Okay. All right. So we want to prove this theorem, and it actually turns out that the proof of this theorem is fairly straightforward. It does not require any major results. It is really just a consequence of the chain rule or U substitution, depending on how you want to think about it. So let's sketch out the proof here. So since alpha and beta are equivalent parameterizations, I'm just going to say they're equivalent. Then there exists a U. Okay, that U is going to map from the closed interval CD into, now before we wrote R, but then we said the range has to be AB, so let's just write into AB, such that U prime of X is not equal, or sorry, U prime of T is not equal to 0 for all T in CD. Oh, sorry, and like, this is the important part, right? Beta of T is equal to alpha of U of T. All right. Well, let's start then by looking at the line integral over C of f d beta. Well, what is that? Well, by definition, right, from last time, we saw this is defined as the integral from C to D of f of beta of t inner product with beta prime of t dt. That's simply the definition of the line integral. Okay. But now note here, right, this function u satisfies beta of t is alpha of u of t. So if that happens to be the case, then one consequence of this is I can take a derivative, right, beta prime of t, and sorry, that these betas and alpha should have hats. So beta prime of t, I need to apply the chain rule. It's alpha prime of u of t times u prime of t. Okay. So I can now substitute in where I see beta here and where I see beta prime here. I can just substitute in those values. So this will be equal to the integral. I'm going to have to do something with the endpoints in a second. So let me just hold on to that for a second. But this is going to be, oh, sorry, no, not yet. I don't need it. These are still with respect to t. So this is going to be f of alpha of u of t dotted with beta prime, but beta prime is alpha prime of u of t times u prime of t dt. Now, let me just note here, right, u prime of t, u is a scalar function. So u prime is just a scalar function. This is a vector valued function. So we're really taking this vector times this scalar, which gives us a vector valued function, inner product with this vector value function. So just so we're clear on what types of objects all of these are. Now I'm going to use one of the favorite tricks from calculus, which is a U substitution. But I've already got U, so let me call this V. So I'm going to let V be equal to U of t. And if I do that, then dV will just be U prime of t dt. And hence, well, let's see, we've still got this integral over C, over the curve C of f dot d beta. All right, that was equal to this. But now if I do this U substitution, this is the integral. Now this is where I have to pay attention to my endpoints. So let me come back and deal with those in a second. This is going to be the integral of f of, this is going to be alpha of v now, dotted with, this is going to be alpha prime of v. And now this u prime of t dt is just going to be dv. Okay. And so notice if I look at this, this looks like, except for maybe I have a v variable here instead of t, this now looks like a line integral of f d alpha. Okay. Now, let's be a little bit careful here. So here, the endpoints were c and d. Now, I'm changing variables so that my new variable v is u of t. So this lower limit of integration, now we're switching from t is equal to c. Now v should be u of c. And the question is, well, what is u of c? Well, u of c, we saw on the previous slide, right? U of c is either a or b. And u of d is going to be the other one, okay? So you sort of have two cases, right? Sort of case one is u of c is equal to a and u of d is equal to b. If I'm in that case, this just becomes the integral from a to b. And then by definition, this is just the integral, the space here. And then by definition, this just becomes the line integral over c of f d alpha. Okay, so if we're in this case, then we're done. And we get that these things are equal. So that's like case one in the theorem. If alpha and beta carve out the path in the same direction, okay, then we get equality here. Now, what if we're in the other case? Okay, so in the other case, u of c is equal to b, and u of d is equal to a. Well, in that case, instead of getting a to b here, we'd get b to a. But then we could swap them and we just pick up a negative sign. Okay, so what we can say here is that, right, you're always going to get either positive or negative this quantity, which is going to be positive or negative this, and you get positive when you're in case one, that's that things are in the same direction, and you get the minus when you're in case two, which is the parameterizations are moving in opposite directions. So that concludes the proof of this theorem. So this is actually, and one of the reasons, sometimes like this lecture was entitled Basic Properties. And, basic doesn't always mean simple, but what it does mean is this all falls right out of the definition, right? We're not really using any high-powered theorems here. All we're really using is some Calc 2. But what we're seeing is that an immediate consequence of the definition of the line integral is that it is independent of parameterization. So if you have two equivalent parameterizations of a curve, then the line integral is going to be the same irrespective of those parameterizations. Okay. All right. Now, I do want to briefly go over a couple of other basic properties. So the line integral, and you might sort of suspect this, it's defined in terms of a Riemann integral. Riemann integral has a lot of nice properties like linearity. So you might wonder, well, does that carry over to line integrals? And the answer is yes. So if you have two vector fields, f and g, both of which satisfy nice enough properties, they're continuous on the graph of piecewise smooth path alpha. And if c is some scalar, then you do get that line integrals are linear. So if you have some constant times your vector field that you're taking the line integral of, you can pull that constant out of the line integral. If you have a sum of two vector fields that you're taking the line integral of, you can rewrite it as line integral of the first vector field plus line integral of the second. And just to give you an idea, right, the proof, we're not going to write out all the words, but the idea here is you just write out what this is by definition. By definition, this would be the integral from some point A to some point B of c times f of alpha of t dotted with alpha prime of t dt. Now, this is a Riemann integral. So for a Riemann integral, you can pull this constant out. And now this is just now c times this, which is the line integral of f d alpha. So again, these just follow by writing out the definitions and applying these properties of Riemann integrals to the Riemann integral formulation. Okay, same thing for breaking it up over a sum. A couple of other properties. So you get additivity over paths. So if you have a path alpha, so let's say you have some path alpha here. Okay, and let's say you want to break it up into two pieces, say alpha 1, and maybe alpha 1 goes from here to here. And right, these points really should be filled in, but to help. So there's alpha 1, and then some other path, alpha 2. Okay, where again, you have to have these conditions where the terminal point of alpha 1 equals the initial point of alpha 2, and alpha 1 union alpha 2 gives you alpha. Okay, so really you're decomposing alpha into two pieces, alpha 1 and alpha 2. Then the line integral of f over alpha is equal to the line integral of f over alpha 1 plus the line integral of f over alpha 2. To prove this, again, you do the Riemann integral formulation, and then you're essentially using the property of Riemann integrals of the integral from a to b of g is equal to the integral from a to c of g plus the integral from c to b of g, where c is some point between a and b. Okay, so this again, it really is, these are really just analogs of properties we saw for Riemann integrals. The final one actually, it actually falls out of the theorem we proved earlier, but it's just sort of a helpful thing to have in the back of your mind. It essentially says if alpha minus just takes the path alpha and reverses it so that it moves in the opposite direction, then your line integrals are going to be opposite of one another. Okay, so here you just need to formulate alpha minus as an appropriate change of parameters of alpha, and then the result falls out of our previous theorem. So again, these are all just fairly straightforward properties of the line integral. Mostly they fall out of either properties of the Riemann integral or properties of the independence of parameterization that we saw earlier. Now, we still have this open question. I mentioned at the end of the previous video, we sort of posed two questions. So the first we've answered. The first was, are line integrals independent of parameterization? And what we've seen is the answer is pretty much, well, as long as you define equivalent parameterizations in the right way, then yes. Okay. The second question was, what vector fields will have line integrals that are independent of the path taken between 2 points A and B? So in the particular case we were looking at in the last video, we had these points 0, 0, and 1, 1, right? And we really looked at two different paths between those points. So we looked at this straight line path, and then we also looked at this, this sort of polynomial path. And we had two parameterizations of the polynomial path, but for that example, the integral over these paths was different. So we certainly already know it's the case that not every vector field has line integrals that are independent of the path taken between 2 points. So if it's not all of them, well, then which ones do? Okay. And one reason we think that it's reasonable to expect that at least some of them might is we have, for the regular fundamental theorem of calculus, right, something like the integral from a to b of g dt is equal to capital G of b minus capital G of a. And what this does, right, is this gives us a way of thinking about the integral of g only in terms of the value of this other function at the endpoint. So it's independent of how t is moving between a and b. Now, we're in one dimension here, so there's not really a lot of room for t to move between a and b, right? There aren't a lot of different paths. But again, it's sort of reasonable to wonder, could I come up with some formulation where I have the line integral of a vector field with respect to some parameterization is equal to, say, some function of f some function f evaluated at, say, the endpoints. Okay, so like imagine this is A and this is B. Okay. And the key here is to recognize that this only worked because capital G, the derivative of capital G was little g. And so what we might want to say is, well, this will work, but only if this vector field is an appropriate derivative of this function f. Namely, if the vector field that I'm integrating is the gradient of some function, then maybe I could write down something like this. Well, in fact, in the next video, we will work to establish this result. This is essentially a second fundamental theorem of calculus for line integrals. And this will begin to help us answer precisely this question of which vector fields will have line integrals that are independent of path.